condition where I forgot to put that x has to be positive, real number has to be positive. Now, it's clear that if x is negative, this is satisfied, but we'll still need x positive to actually prove this result in general. And again, this is an 8th degree polynomial. Nobody can solve this without doing numerical methods. There's not a person alive who could solve this, I don't think, quote, the old-fashioned way without technology. You can use numerical methods to find this and then see if it satisfies this. But again, that's not anything that's too inspiring. Okay, let's move along. Now, just some simple steps here. Since 35 is the numerator of this fraction, it's reasonable to rewrite the initial condition like this. Just add 1 to both sides, you get 35. So at least 35 is in sight. All right. Now the rest of this is slightly unmotivated. I wouldn't know. I've seen these type of problems before, graduate school, and factoring sometimes is useful, sometimes it's not. In this particular case, it turns out to be quite useful. This pair of binomials give you this expression over here on the left-hand side. Now, this next step is motivated by the fact that we do have a fractional constant. And so we divide everything by x to get this statement. So far we're up to here. Everything's equivalent to the given. But what do we do from here? Well, we use this fact here. I call it the truth that x plus 1 over x is greater than or equal to 2. I didn't prove that. Let me go ahead and do that. Y'all, there's something called the arithmetic mean, geometric mean inequality. And for this particular case, it goes like this. You'd have x plus 1 over x all over 2. All over 2 is greater than or equal to the square root of this product, okay? So that would be the square root of 1 over x times x. Now we know that x equals 0 couldn't be part of the situation here. It doesn't satisfy the given equation, so we can rule out x equals 0. So this is just equal to 2, or equal to 1, right? 1 over x times x, if x is not 0, is equal to 1. So this is equal to 1. And you can see how this works out. You can see why. This would all imply that x plus 1 over x is greater than or equal to 2. Okay? That's just a simple application of what we call the arithmetic mean, geometric mean inequality. You take this 2 to the other side, and you end up with this. Now, the reason why I said that x has to be greater than 0 is that's what the arithmetic mean, geometric mean inequality does not hold for negative values. You can see the problems you would have taking square roots of negative numbers, perhaps. All right, so that's why we wanted x to be greater than 0 at the beginning. It's clear that if x is negative, it would satisfy this, right? Any negative x would satisfy this clearly. But for the rest of the processing to be justified, we have to assume that x is greater than 0 for the positive numbers, okay? Now, the rest of this is fairly routine. I just wrote down the work rather than take the time to write it out myself. But notice that what happens right here, if you divide by 2 and multiply by x, you actually get what we're looking for. You would get 35 over 2. Okay, so I divided through by 2, multiplied by x, so that would make this greater than or equal to x to the 7th plus x. And of course, this is just written in the other way of what we're trying to prove, okay? Some people with dyslexia have trouble with this kind of stuff. But notice that this object right here, the inequality we're trying to prove is certainly equivalent to this, right? Sorry, I can't keep it all on one screen. But we were trying to prove this, and we got this. So we can write down, thus we have demonstrated, QED. And that's that, folks. And I thought this was kind of a hard problem. I wouldn't have been able to figure this out. I remember working on this problem for 2 hours when I was a grad student, and I had to look at the solution. It's just the path isn't clear at all. So if you struggled at the beginning figuring out what to do, some of the steps are unmotivated. I tried to motivate it as much as possible. But even knowing to factor this is not clear, really, until you notice what you're trying to prove. So maybe some of you would intuitively or instinctively know to do this factorization, but that's key. And also recognizing that x plus 1 over x is always greater than or equal to 2. Okay, that's important for this to work out. Okay, so, and again, it's I guess this would be of interest to some people. This is an initial condition, and whatever the solution to x is, notice we're not within a million miles of solving for x, but we know that any x that is a solution to this equation, any real valued x, order doesn't make sense for the complex numbers, right? But any real valued solution to this equation would have to satisfy this. So if any of you have the time, you can numerically solve this. Let me know if you know how to solve this octic equation in any other way. I don't think there's any way even the best mathematician in the world can solve this unless they use numerical means, okay? Because there's no known formula. Galois proved that, and it's just impossible to solve it. You could try the rational zero theorem, maybe that would you'd actually get lucky, but I doubt that. You would be trying 1, 2, 17, 34, and plus or minus, all that stuff. But I don't think any of those are solutions to this. So that would be the only savior here if there happen to be integer solutions to this. But I don't think so. But in any event, thank you for viewing. Hope you enjoyed it.